Chris Keegan, who I've known for quite a while. D. Echols is our other presenter. I'm sorry.
Gotta get the fine points on this before we start so you don't mess it up too bad. So the question is, why am I here? It's because every once in a while you find something that works and you want to kind of let everybody else know that it's working. And to do that, we'll go over some topics. You remember the first day you were here, you talked about Darth Vader and the mild-mannered young engineer. Well, I'm not the young engineer. Anyways, but things have changed since I was young, because now we work very closely with our vendors, because they have a lot of good stuff, and this was one. So I saw Di back in Denver about a year ago, and she was the new rep for Fatigue Technologies, having taken over. So I asked her a question, said, how many states are using this tool? And I put her on the spot because she didn't know. So she had to go back, go through all their data to find out. And at that time, there were 10 states. And this has been, I learned about it, I think, back in 2012, Subcommittee on Maintenance meeting in Seattle. And Fatigue Technologies went across the bridge to where we were having our meeting from Renton, because they were pretty close. Their number one, probably, customers are Boeing and Airbus. And I'll tell you how that fits in later. At the time, maintain bridges as the state bridge maintenance engineer. And one of the most frustrating things is to send crews out to do a job, and then after a bridge is inspected, you have to send them out again to do the same job, because we were chasing these fatigue cracks. Now, the state of Washington does not have a lot of steel bridges. We like concrete. We have real good aggregate, so we build everything of concrete if we can. But we still have a lot of older steel truss bridges. The steel stringers have reached the end of their fatigue life. They're cracking. We have some of these arch bridges, bowstring type arches. They move a lot, and we've had a lot of trouble with the stringers on those cracking also. So those are our main areas. Not a whole lot of bridges, but I hate to waste time sending crews out just to send them out a couple of years again. So the current repair method at that time was a crack arrest hole. That's what the bridge office told us to do. You go out with your dye penetrant, you find the end of the crack, you drill a hole, and then you wait for the next inspection cycle. And we do that over and over again, and we just chase the crack. And so you ask the bridge office, well, what do we do? Well, drill a bigger hole. So we find the end of the crack, and we drill a bigger hole. And then next time it would propagate, they said, well, drill a bigger hole. So we're up to about a 3/4 inch hole, maybe a 7/8. Then they said, okay, we'll put a bolt in it and tighten it up like crazy. Try to put some compression in that steel. So we do that, and then next time it was inspected, the cracks seemed to propagate beyond that too, so then we put a plate on it. And now we're good, because you can't see the crack anymore. So at the point you say, there's got to be a better way. There's got to be a better way out there someday. So her predecessor cornered me at the Subcommittee on Maintenance meeting, and he had gone to a TRB meeting, and he was touting what they do for Airbus and Boeing to keep cracks from occurring. And he said some lady came up to him and asked him, well, why aren't we using this on bridges? He said, I don't know. Guess nobody ever thought of it before. So he put it in his mind, he went back to Renton and started putting some things together to present this to state bridge agencies. And we were one of the first. Jeff over here, he was at the same meeting. Like all state governments, the first thing you have to do is be able to buy something, and how do you buy it? It's not easy. So first of all, it took us close to a year to prove that this was a sole source. So we could actually go out and buy it, pay them what they ask, and then we can go use it. So that was one of the first hurdles we had to go through. So that was it. And then before we go any further, how many of you are flying out of here this week? I want to see your hands. Okay. Well, what Len Reed got me when he told me, he says, this is what keeps the wings from falling off the airplane. Well, that meant a lot to me. Says, hey, if it can do that, maybe we take a risk. We'll try this, just give it a try. So we did. Soon, about a year after that, I think, the Satsop River Bridge failed. If you remember that, got hit, the whole span failed. And that helped me two ways. One, it got me money for cleaning bridges because it hadn't been cleaned. When you took the dirt off, the paint was blistered and removed and rust. But the other thing is there were cracks that had to be repaired. And this was the first bridge we actually used the Stop Crack X tool on. And that was put in about 5 years ago. And for the state of Washington, I'd found out that of the close to 100 different repairs we've done with the tool, none have propagated past the bushing. And after all the frustrations we had with using the crack arrest hole, I says, well, this is working. That's why last May I asked Di, well, how many states are using it? And she said 10. That's why I said, I have to be here at this meeting until the other 40 or so states, this thing works. So, if you have fatigue cracks, use it, because it works. So, those are our current repair methods. I think I missed a lot of the stuff we had here. Time-wasting repairs, I cover that. Need to find a better way. Good results. Check with FTI. As of, I'll cover the poll in a minute, but as of now, we have 3 more states that have purchased the tool. And this doesn't mean there aren't other states that use it. These are the states that have, maintenance crews. And so they buy the tool for their use. Some states specify it in contracts if they have a lot of fatigue cracking in a bridge and get the contractor to do the work. Find the crack, grind it out for small cracks, longer cracks, drill a crack arrest hole, polish the hole, chase the crack, try the bolt, and after next inspection, repeat. Here's a picture of, this is Satsop River Bridge, 12051 South, end of the crack. This was one of the last crack arrest holes we put in. You can see where the hole is. And you see year after year after that, as it's inspected, how the crack has propagated.
Good afternoon, everyone. Thank you for being here today. And I really appreciate Chris and Washington DOT. We were sitting in the Denver airport last May, and we started having this conversation. And I told him I was a little frustrated because I didn't understand why we weren't doing better. And I understood why, if many of you may know Len Reed or remember him, he spoke here 4 years ago. But I think that for whatever reason, Len was a guru for us, and he was just all over the place, so we could never concentrate on it. So I'm trying to concentrate on this and trying to get the word out. So I really appreciate Chris's help in doing that. But enough about that. I think I would first like to explain what it is exactly that we do. So if you haven't been by and talked to us before or didn't come out and see our demo this morning, what we do is really elegantly simple. It's an aviation-derived technology. Back in the 50s, there were some really bad decompressions and aircraft accidents that were happening. Bad decompressions that resulted in accidents, and they were coming from fatigue cracks around fastener holes. So Boeing started working on what can we do to protect these fastener holes from cyclic fatigue, and they came up with a methodology called cold expansion. It's basically like a really deep shot peening or a mandrelizing, but you get much, much deeper. You typically get about a radius or a little greater around the hole that you're able to actually protect from cyclic fatigue. So as Chris said, FTI has taken that technology and done many things with it, but as Chris pointed out, somebody told Lynn, hey, why can't we do this with crack arrest holes and protect them from cyclic fatigue? Because a crack arrest hole works at that moment. You have reduced the stress intensity factor at the tip of that crack at the moment you cut that hole. But then your structure still continues to be under load, and that load continues to work on the tip of that crack, right? So that crack is going to propagate. You're going to get a through crack, and then it's going to reinitiate on the other side. So what we do instead is put that hole, that crack arrest hole, into a zone of residual compressive stress. And that is going to shield the crack from the cyclic fatigue loading. Very, very, very simple to do. And the first 2 steps you're pretty much already doing for the most part. Locate the crack tip. You know how important that is. You got to find that crack tip, and it's not necessarily going to be on the surface. So whatever method you currently use to find the crack tip, you still employ that method. The next thing you do is drill the hole. So we want the hole to be very specifically sized and very specifically placed. So our holes, like, okay, so sidebar for a second, many of you have told me in the past, and I'm not a stress person, so I'm just getting it from when I'm talking to people like you, that you look at the length of the crack and you have calculations to determine the size of the crack arrest hole that you want to drill. We say you don't have to worry about that. You're going to drill a 1/2 inch hole. Okay, so you're going to find the tip of your crack, you're going to lead it by 5/16, and then you're going to drill a 1/2 inch hole, leaving a 1/16 of a ligament between the tip of the crack and the crack arrest hole that we're putting in. You're then going to confirm that the hole size is correct by using a little check gauge, and then you're also going to confirm that the mandrel has not been worn. Put the bushing on the mandrel, pull the whole thing through with the hydraulic operation, and you monitor it. It's really just 2 additional steps beyond what you're currently doing to put in a crack arrest hole. It's very, very easy. No special training required other than reading a spec and maybe having somebody watch somebody do it once, and then it's good. It's really very easy to do. And it works. So we've done some finite element analysis on this, and we've also done lab testing, and we have many, many repairs out in the field when, as Chris pointed out, no issues, and I've talked to several other DOTs who said they've had 0 issues. So let me just show you some of our FEA analysis that we did. So our model assumptions for the FEA was that we were going to be an A36 steel, which is very, of course, what you guys are mostly using. Our baseline is the top with no load, and the bottom picture there is our baseline. It's a residual compressive stress has been put in, so this has been a stop crack EX repair, but with no load. So you can see on there we've got the area of compressive stress actually surrounding the hole, and you can see the crack tip. Now if I want to put it under load, the top picture there is a crack and a crack arrest hole with no residual compressive stress. And you can see that the tensile loads are right on that crack arrest hole. That's why it's going to propagate. That's why it's going to go through to the other side. The other two you can see are the residual compressive stresses are there, and so it's protecting that hole from the impact of cyclic fatigue. You will eventually grow that crack to the hole or to the bushing. And you can see that in the picture on your bottom right, okay, or I'm sorry, bottom left, but it's still going to protect it and it's not going to exit the other side. We did some, well, we didn't do it. We actually asked Metal Fatigue Solutions to help us, and Mary Beth Maselli, we're grateful for both of them, to help us do some independent testing. They went to Southern Utah Engineering and helped us set this up for a test without our fingerprints on it. We wanted this to be very objective. So they took 7 dog bone coupons, and you can see the dog bone coupon diagram there in the bottom of the slide. We had them pre-cracked, so we cut a notch in it, put it in an MTS machine, loaded it until we got a 1/4 inch crack. Once we had that 1/4 inch crack, we repaired 3 of the coupons with a traditional crack arrest hole, and we repaired the other 3 with a stop crack EX. Here are the results. The point was to run the test until we had a 1/4 inch, or until we had a crack reunation on the other side, or 4 million cycles, whichever came first. And you can see the results on the bottom there. The 3 crack arrest holes, none of them got past 440,000 cycles, whereas the stop crack EX holes all were, the tests were stopped at 2 million cycles with no crack reinitiation. Somebody decided, hey, let's take our spare dog bone coupon and stop crack EX it and just run it. And they ran it just kind of like, hey, let's just see how far we can go. And I think at some point when it got to 20 million cycles, somebody said, we're wasting lab money, let's just stop it. So they stopped the test at 20 million cycles. So that's pretty impressive. So between, you see the FEA and then you see the lab, but really in my mind, what is really the proof in the pudding is when guys like Chris Keegan say, hey, we've put in hundreds of holes and we've not seen any propagation. Here's just some examples. The first couple that you see there were some of our original case studies that we did. The Manahawkin Bay Bridge back in October of 2011, the Lincoln Tunnel Interchange for the New Jersey Turnpike Authority, and then the Delaware River Bridge for New York State DOT. I was able to actually get in contact with New Jersey and New York and confirm that those repairs are still great, no crack propagation. I haven't been able to hook up with the Turnpike Authority, so if anybody's got a good contact, I would appreciate it. And then also the Satsop River Bridge that Chris was just talking about, repaired just this last fall.
So after I got back from our Western Bridge, I'm all excited. I'm a preservationist and trying to figure out now what's my next step and how do I get to this meeting and what do I need to do. So the first thing I thought was we should survey the states, find out what they do, why they do it, and so on. So finally put my questions together, sent them out. We had 18 replies from 17 states. Thank you, Maine, for replying twice. Ben? And for 14 states, they grind out small cracks, and they use crack arrest holes for longer cracks, and then they plate the crack. The size of the crack arrest hole varied from 1/2 inch to 2 inches. One state, the hole encompasses all the crack or cracks. They just take everything out that's cracked. Then they plate the hole. Results were mixed. For several states, what they're doing is working. There's no propagation after they're using the crack arrest hole. For others, some of the cracks continued after 2 to 4 years. 5 states that replied actually used the crack arrest tool. And 3 at the time were in process of purchasing. And the states that really use it, especially West Virginia, Arkansas, state of Washington, Virginia, about 4 or 5 years they've been using them now. There's been no problem with the bushings. They've held up. Whereas if it's anything like what we've had, after the next inspection, we're back out there doing work. And not only that, but our bridge office has bought into this. A lot of times their maintenance folks go out and do stuff on their own. And then we try to back it up with bridge. Well, they jumped right in on this thing. And so this is actually our official stamped repair. If it's a 1/4 inch or less, we grind it out. Beyond that, we use the crack arrest hole. And if the hole is greater than 6 inches, we still put a plate on it. This is, again, the Satsop River Bridge. The hole was beyond 6 inches. Here is kind of a simple diagram of the plate. This is not what we did. Here's the plate that we put on over the top of this. And not only are bridge engineers believers in belts and suspenders, maintenance people really are. So they put plates on both sides. So there's a lot of meat in there. My conclusions, the states that have used the tool have found it effective in stopping fatigue cracks. No state that answered the survey reported that they had a crack move past the bushing. And there's a large cost savings in not having to redo a repair. As Di said, this is a very easy repair. It's the access to the repair that's expensive. You use snoopers, under-bridge inspection trucks, different ways to try to get to where you do your work. Once you get there, it's a fairly simple, easy process to do the crack X repair. When I started this off, we have 6 region crews for doing bridge work. One jumped right in it. They grabbed the tool. The Northwest took off. I had another region that didn't want to do it, so we had to force them into it. But all the crews, now that they're starting to use it, find it quick, easy, and it works. And once the repair is done, they don't have to go back. So they like it. Yeah, so there's a very large cost savings in not having to go back. The cost probably is about pretty close to the same. And anyways, it works. So if I can convince you, I like to say, once you do it, once you start doing this, I think you've got your fatigue cracks pretty well taken care of.
So I saw one of the points was that it works, the assumption was it was for grade 36 steel. How does this translate to different grades of steel, higher and lower? Is it a matter of having a different bushing made of a different material? Or?
Yeah, that's a great question. So anything above 60 KSI, we recommend a different bushing. So we have what we call an A bushing and a B bushing. So here's a little secret though. If you use the wrong bushing, the bushing might fall out, but you're still going to get that residual compressive stress. So, because you're not always quite sure exactly what your grade is without doing some kind of testing. So we typically sell the A bushing, which is made of stainless Crest 304. But if they tell us that their bridge material is stronger, then we'll sell our B bushing, which is made of Forgive me, I believe it's 17.4. So either one of those, but we just respond to whatever's needed.
The question is, I understand that you can purchase this whole equipment from FDI, or am I misunderstanding that? If so,
I don't want to make this I'm feeling a little awkward because I really wasn't trying to do a sales pitch. But if you want to discuss that, please come see me afterwards.
I can make a,
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.